So in the previous video I showed you that this differential equation we've been working with is both linear and shift invariant. And for systems that can be described, or for systems that have these properties, you can completely describe them using what's known as the impulse function, or Green's function. Green as in the color Green's function. Okay, so what does this mean? What is Green's function, and what is the impulse response of a system? So Green's function, which we will call h of t, and we will draw in green, of a system L, is the response of that system to a delta, or Dirac delta function. Now, some of you may not know what a delta function is, and I will post a couple of references for you to learn about that more. Just briefly, however, a delta function will look a little something like this. So a delta function, in this case it's a function of time. Let's say, and we have a variable x on the y-axis. Okay, so a delta function is going to look like this. It is 0 everywhere. 0 everywhere except right at time equals 0. It is infinitely large. And if you integrate the delta function over all time, so if you integrate the area under this curve, you will end up, so from negative infinity to infinity dt, you will get 1. So this is what the delta function is. It has a nice, some nice properties. It integrates to 1, and I will, again, post some references. So, it's sort of a weird function, and for those of you who don't necessarily come from a math background, this might be sort of hard to wrap your head around at the beginning. But there's a lot of good explanations of it on the web, thankfully. So what's nice about the delta function is that you can use it to represent any input into your system. So if we have a step current, let's say, this is the input into our neuron, how can we represent this as a series of delta functions? Well, in the beginning here, we just have delta functions of amplitude 0, and then starting at this time here, we can have delta functions of the appropriate amplitude, and we can just stack them next to each other in an infinitely dense manner, and then at the end, we just have them at 0. So you can represent any input signal as an infinite sum of appropriately shifted and scaled delta functions. So, and if you think about this, this can be true for any impulse or any input that you give. So if you have a sinusoidal input, you can just stack up delta functions here, and then you can multiply them by negative here. So you can essentially just tile these delta functions and build up any input that you want. And this is how you would state what I just told you mathematically. This is what's known as a convolution between a delta function and any input signal. So the input signal x of t, which in our case we're sort of thinking of being I, and j, that can be represented by a bunch of delta functions which are shifted. So you're shifting the delta function in time by some factor t prime, and you're scaling it according to the magnitude of the input function at that time t prime. So you might be wondering why we would want to represent the input in this way, but it's actually quite simple, and we're actually very close to solving for the output of this system. So if we have linearity and shift invariance, which I will denote SI, if we have those properties, then the response of the system to each delta function can sort of be considered independently from each other. And if you go back and look at the properties of linearity, that's exactly what those properties are saying. You can either have one step function, or you can equivalently think about this as a bunch of impulses where that are stacked up sort of infinitely close together, and they continue down so that they span this whole range of this step function. So we can consider the output of the system, or y of t, as a sum of all of these inputs which we have represented as delta functions. So if you've followed the logic so far, you'll realize that this is the output of the system, and this is how we can solve for the output of the system, y of t. And the only difference is that I've replaced the delta function with this with Green's function, which again I've drawn in green. And this makes sense because what I've told you before is that Green's function represents the response of the system to a single impulse, or a delta function. So once we know the response of the system to an impulse, then all we have to do is add together the responses to this infinite number of impulses that we've sort of postulated in this equation, and then we have our output y of t. And what's nice about this approach is that before we just numerically solved for what the membrane potential would be, but if you follow this approach, this is, an exact expression for what the membrane potential should be. You might not be able to solve it because you might not be able to evaluate this integral effectively, but this gives you an exact definition, or an exact expression to define the output of the system. So the last thing that we need to figure out is what Green's function looks like for a passive neuronal membrane. And I'm just going to tell you that Green's function for a neuronal membrane looks something like this. You have an impulse, and then it decays back to its steady state, which we've been calling E. And there is, if you're really into the math and you're following the math really closely, you might realize that having a non-zero membrane potential sort of actually violates this linearity property I've been talking about. So the way that we get around that is by setting E equal to 0. And if you do that, this system that we've been talking about is strictly linear. So for those of you that have been following the math very closely, I apologize if I've been a little obscure on that point. I'm just sort of trying to give you like the broad, the story in sort of broad brushstrokes. If you're interested in learning more about Green's function and this approach, I highly recommend you pick up a copy of Christoph Koch's Biophysics of Computation book. That actually, pretty much I've been using this book to make these last 2 videos and been following it pretty closely, and he goes into a little bit more detail than what I've been able to do in this short time. So if you are interested in this, you can pick up this book. It's a great book to have anyway, and I'll probably be referring to it quite a bit if I continue to make these videos. So that's pretty much it, and in the next few videos I think we're going to look at a couple of numerical simulations of this differential equation and start to just look at more examples and develop an intuition about how this system behaves. Thanks.